Hey everyone, welcome. Can you hear me in the back without a microphone? Am I okay? Great, okay. That way I can be a little out of your way and show my new blue laser pointer. 450 nanometers. eBay, China, $60, no problem. So, I got 6 pointers. I'm a physics nerd too, even though I'm an aerospace engineer. Can we get the lights a little lower? I think the graphics will sizzle more the darker we can make it in here. Let's see. So I had the great privilege of working on Curiosity as a part-time job. Boy, what a heck of a part-time job. Very demanding part-time job. I've been on the Cassini mission to Saturn for over 15 years, since before launch. I'm the head propulsion engineer on that. But when I found out that there was a new mission, sexy mission, that I'd get to be on camera, I said, oh, I've got to work that too. And so they let me come work that mission for a couple of years. And little did I know how much work it would be. But it was really the perfect scenario 3 weeks ago, because if it would have worked fine, which it did, I can claim excessive credit for this mission. So I could have done it without me. Definitely not true, but I was pretty heavily involved. And if it failed, I could have disavowed any knowledge of Curiosity. No, I've been on Cassini the whole time, flying around Saturn. It's a shame you guys failed, but we had a wonderful last few weeks, as you might imagine. I'm finally recovering, from the celebrations. But today we'll talk a little about Curiosity's story and what it has to tell us. I did work on the last set of Mars rovers also, a couple of years on that, cut my teeth there, and that was a great experience too, and I'll definitely talk about that a bit. We've got tons of slides, some videos to show. I'll try to leave some time for Q&A. Let's go to the next graphic. Okay, so why go back? We've been to Mars before. Pathfinder had a little cute rover about the size of a child's wagon or microwave oven. This was in the mid-1990s. A technology demonstration mission. Can you land cheaply on Mars? Cheaply being about $250 million. And we did it. So I know it doesn't sound cheap, for those of you paying tuition and things, but by NASA standards, that's a cheap mission. And it worked, and it's supposed to last about a month or so, and we ended up about 3 months on Mars. And we landed on July 4th, 1997. So celebrated the nation's birthday and had this cute little rover that did some very rudimentary science, but a total success, including the bouncy airbag landing and all that. That was wonderful. So we came back with, NASA said, that's great that you can do a mission for $250 million. Now do 2 of them for $250 total. So we tried that in 1999. We went 0 for 2. So we found what the breaking point is. We cannot do a Mars mission for $125 million. They won't work. So at least we're 0 for 2 so far. We had the Mars Climate Orbiter. Did you ever have a professor take points off because you didn't write your units down? Like, you knew which units I had. Oh, really? I have 125 million reasons why you should write your units down. So Mars Climate Orbiter was lost due to the infamous, it was not inches and meters or feet and meters or whatever. It was a torque unit. It was foot-pounds versus Newton meters of torque. Or it was really in the force. It was newtons versus pounds. If they'd had any engineer that had any time at all would have noticed that their thrust prediction factors were off by a factor of 4.45. That sounds kind of familiar to us physics fans, doesn't it? Newtons to pound conversion. But they did not have the personnel or time. We had fist fights and all kinds of things, blaming each other. It was horrible. And when we lose spacecraft, they send in grief counselors. It sounds like a joke, but we anthropomorphize these robots. They are very much, sometimes we spend more time with them than our own families. So, unfortunately. So when we lose one, we grieve. We go through the 5 stages and all that. So they send in the grief counselors. And fresh off that failure in September of '99, we tried Mars Polar Lander, and it went 350 million miles, got to the last 120 feet above Mars. It accidentally sensed that it was on the ground, a flight software bug, shut down, and then free fell and landed at about 50 miles an hour. So, the first 350 million miles were perfect. It's that last 120 feet that killed us. That's kind of sad, isn't it? So, what a dark day for NASA and JPL. But we came back, and they said, let's try again. Now, through here, we had the Columbia disaster, too. I think that was February 1st of '03. Does that sound right? So NASA was in a real dark place in about the summer of 2003. And we went to the next set of Mars rovers, Spirit and Opportunity, and NASA said, no pressure, but these have to work. The sake of not just JPL, but all of NASA's in line here because of the Columbia disaster. Okay, no pressure. Well, we landed those 2 rovers, the twins, in January of 2004, and they both worked. And what a great triumphant comeback for NASA. And I worked those rovers too. They're about the size of golf carts, Spirit and Opportunity. And they were supposed to last 90 days, 90 Martian days. A sol is a Martian day. It's about 24 hours, 39 minutes. And I'll talk about that later, because that means if you're working a Mars rover, you have to go on Mars time, right? So you come into work 39 minutes later every day. It sounds great. Ooh, extra sleep. College student, I could always use that. Well, if you're sleeping 8 hours a night, you're actually losing sleep because your day's longer. So it's really hard. People with families trying to get a bite to eat, going on Mars time is really difficult. We had special Mars watches made back for Spirit and Opportunity. We went to this European watch manufacturer down the street in Pasadena, and really craftsman, And it was said, can you make a watch that loses 39 minutes, XX seconds every day exactly, and can be accurate to a second over a year or so? And he's like, I'm a craftsman. I cannot. 39 minutes a day. I cannot make a watch that bad. It's horrible. Oh. Well, here's a few more $1,000. Okay, I'll have you some in a month. No problem. So everybody had Mars watches. Now I was looking. Where are the Mars watches for curiosity? I haven't seen any yet. And they said, dude, get with the times. It's all apps now. It's all iPhone apps for Mars time. And I said, well, I wouldn't know. Here's my cell phone, a track phone. So I'm pretty old school here. And I got this even under protest. So apparently no Mars watches anymore. You can just get a Mars app to be on Mars time. I definitely digress a little bit there. Before we get going to curiosity, there's a few fun stories from that I like to tell back from the Opportunity and Spirit days. The first landing went successfully January 3rd, 2004. So 3 weeks later, in comes Opportunity. And a couple of politicians just said, I'm going to go to the landing at JPL, because they had nothing to do with it, but they can show up at JPL and get credit for something that, that sounds like a politician. Get credit for something that had nothing to do with it. Be on camera with a winner that would probably work. And indeed, both rovers did work. Opportunity ended up working. So our fearless vice president at the time, Al Gore, showed up, as did our California governor at the time, who we might remember, the Terminator. And Jay Leno's joke was, all the robots came to JPL for the landing. So those guys are kind of stiff. That's a good joke, Jay Leno. That's pretty funny. So they admonished us. They said, absolutely no photographs, no autographs, leave them alone. They want them in and out. And I was like, I can't do that. I collect photos of celebrities. I didn't dare try a photo. I did meet Al Gore briefly, but I said, I want to meet the Terminator. What am I going to do? And I said, I can't get the picture. I'll get fired for that. But maybe I can find a way to meet him. So he's coming down our aisle in Mission Control to wish us well. And I said, I'll hop in the aisle and walk his path. So he can't get by without saying hello. It'd be rude. So he looked me up and down, didn't know what to do. Congratulations to you and your team. You're doing marvelous work here at JPL. So anyway, the dime store accent's not so good. Well, then I told my friends. I was very excited. Meeting the Terminator and all that. And of course, doing a little imitation of our meeting. Then the phone rings in Mission Control. Hello, it's your mother calling. Hey, Mom, we landed 2 for 2. We're on Mars. Yeah, we'll talk about that if you're not fired, pal. I was like, what do you mean if I'm not fired? We landed on Mars. I can do anything, She said, well, I saw your little stunt meeting the governor. That's one thing. But then, imitating him and doing the voice, I was like, you're in Kansas. You're 1,500 miles away. How did you hear me doing that? She said, on CNN, because they have the live mics in the room. Watch those live microphones, people. If we haven't learned it from the politicians, learn it from me. And I wish that were the only colorful, scary story from Mission Control. It is not. A month before landing those 2 rovers, we have our cordless headset microphones on. We're never bored there. It's NASA. It's really fun, cool stuff all the time. But it's about as boring as it gets. We're just turning the spacecraft a month before landing on Mars, pointing it to the Earth to communicate with the crew stage. And I have an attitude control engineer next to me. We're looking through the screen, the main JPL Mission Control, and NASA TV is on the screen in there. I can't hear it, but I can see it. And it's a program I've seen before. And so I knew it was an outreach program, actually, and had a very nice-looking young lady from NASA Langley in Virginia. That I'd seen her before. I had a crush on her. So I poked the guy next to me. I wanted to point her out to him. I said, look through the glass there. I said, there's that NASA babe I like. She is so smoking hot. And then I go back to work and the entire room's frozen. They're like, propulsion, open microphone. My headset, that was one of the first pearls of wisdom I chose to share, on the open mic. And dead silence in the room, hundreds of people in the room. It went out beyond that room even. And I wait, dead silence, 5 minutes. I hear behind me, propulsion mission manager here, big boss, right? I was like, yes, go ahead, mission manager. This is it. Time to call back to Kansas, right? He's like, I thought you'd like to know. I looked through the glass and turned a no ring on the left hand. So. Wonderful detective work. So I dodged another bullet there. Despite these major gaps, somehow they asked me to come back and work Curiosity. Here we are back getting ready for launch. We've been before. Curiosity is a big bad rover. It's bigger than a Hummer. It weighs a ton. Why do we want to go back? We've been there before. Well, we have a robot field geologist. That's what we've seen with the Mars Exploration Rover, Spirit and Opportunity. By the way, this Spirit and Opportunity was supposed to last 90 days. Spirit got stuck in the sand after about 6.5 years, and Opportunity is still going 8.5 years into its 3-month mission. So, not too shabby. Yeah, American colors. You say we can't do it. For $400 million each, but other than that. So we've orbited Mars. We have great details now to beach volleyball size resolution, 1-foot resolution on Mars. We want to get to that, an interesting site from orbit, have a long life, mobility, remote sensing, contact science. The new stuff with this rover, we have a chemistry lab with us because our chemistry department is sponsored by visit. Yeah, chemistry, let's go. All right, that's why I'm in propulsion. I was a total pyromaniac. I could fill the whole hour just with nightmare tales from melting holes in my street and making laughing gas and making homemade tear gas and all this. Don't try this at home, kids. So, but anyway, I think that's why I got back into propulsion. A little bit of a pyromaniac, and that was a way to contribute. So we have a geochemistry lab, mobile geochemistry lab. We're searching carbon out. We could get part per million or even a few part per billion sensitivities on some key molecules. Integrated science team. We can process the rocks. We have ovens. I'll talk about a lot of the science instruments later. But that's the neat thing about this rover. Scientifically, this is not your dad's Oldsmobile or whatever. This is a really cool, very capable scientific robot on Mars. Next slide, please. Okay, so a little hard to read. It's great the room's dark. It does help a lot. So here are our science objectives. Assess the biological potential. Let's land in a place that might have had biology. It had liquid water. Let's inventory the carbon. Let's look for the CHNOX. We've heard that, right? Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. The 6 real key elements for life. You need other trace elements too, selenium, a bunch of others. We want to see the features that might have been represent these effects of biology. It's not looking for life, but to see if the conditions were there and if the organics are there. If other missions have been said to be follow the water, this is follow the carbon. That's like the soundbite version. We want to understand the geology and geochemistry of the landing site. Chemical, isotopic, mineralogy, process that have formed. We're looking for past habitability, landing in a place that had liquid water. Assess the long-term timescale of the atmosphere, the CO2, see if there's methane coming off, broad spectrum of surface radiation. This is the RAD instrument provided by Human Space Flight because they said, you can fly us for free, we'll give it to you free, but we want you to characterize the Martian radiation environments before we put astronauts there, so we know how we have to shield them, how thick the spacesuit, where are the energy levels, in what energy bands, how strong is it, how variable is it. So they're hitching a ride. This is the way human and robotics are trying to cooperate a little more. Next slide, please. Okay. So I put USA, it's an Olympics year, and it's an election year, and all that, and this happened during the Olympics. But the real reason is the Russians have tried to land on Mars and have failed every time. They had one lander that lasted for 20 seconds on the surface. So that's a quick science mission. It keeps costs down, but they didn't get much science in their 20 seconds on the surface. And you do have to feel badly for them. We've had a few Martian failures, but a lot of Martian successes too. And this is a 360 projection map image of Mars and where we've landed before. So Viking 1 was summer of 1976. They tried to land on the bicentennial of the U.S., but we had a big dust storm. So we had to delay to July 20th, and that was the 7th anniversary of faking the moon. I mean, when we landed on Mars. I would never say that, not with Neil Armstrong, may he rest in peace. Very sad week at NASA, of course. Viking 2 landed more about 45 degrees north latitude. These were RTG nuclear batteries, no solar power, so we didn't have to worry about being near the equator. And these lasted 5 and 6 years. So those nuclear batteries were great. Some of these other Mars missions didn't last nearly as long. Then we went, let's see, the next one was Pathfinder. This was the little cute Sojourner rover, mid-1990s. Opportunity and Spirit. Notice they're 180 degrees apart in longitude. That's so they don't compete for our love. One of them's on the backside of Mars in the dark, sleeping, while the other one's talking to us. And I was thinking, Imagine if you were a parent and you had 2 kids and one kid was always sleeping while the other was awake. What a great parent you can be. You can devote all your attention to be parent of the year and everything. That's what we had to do because we don't want our 2 rovers fighting for our love and our attention. So we put them on opposite sides of the planet. Okay, off to, let's see. So Spirit of Opportunity, we're here. And that takes us to the Mars exploration, or the Mars Science Laboratory, Curiosity. We had 100 landing sites, down to 50, down to 25, 8, 4, 2, and 1. These were the final 4. Marworth Vallis, barely pronounce that, Holden at Eberswalde right next to each other, and Gale Crater. Next slide, please. So here was, I can actually read it. We finally have a dark room. I've been struggling in schools all yesterday and today. You probably can't read it, but I'll read the highlights for you. These are called the landing ellipses. The little black elliptical body is our 3 sigma uncertainty of where we can land. So the first criteria, you have to pick a landing site that is safe over the whole landing ellipse. And that's really hard when the landing ellipse is big. And my next slide is going to talk about how the landing ellipse has shrunk over subsequent Mars missions. But this is also a topography map. So blue is low, like where water would have been when Mars was warmer and wetter billions of years ago, as it was. So everywhere we're landing is pretty low and well, this is not so much, but I'll look at that in a second. So Eberswalde, near the equator, it has clay-bearing delta, like a river delta, like the Mississippi at New Orleans. So it's an ancient river deposited sediment, possibly to a lake. I'll skip Gale for the minute. Holden is another crater, alluvial fans, flood deposits, possible lake beds, clay-rich sediments in a low area. These are liquid water, great environments. We're going to try to read the layers, look for clays and sulfates. We have Marworth Vallis here. Exposed layers with different mineralogy, including at least 2 types of clays. So if you want to go straight for the clays, you go here. And then there's Gale Crater. And this ended up being really wet because it had everything. It had a river delta, it had clays, it had sulfates. To boot, if we could land in this crater, there's a central peak called Mount Sharp, 16,000 feet high. So this would be a national park on Mars, absolutely gorgeous. And we're going to start climbing that mountain with its exposed layers, kind of like the Grand Canyon, different geology and exposed layers, clays and sulfates, and get at this carbon and water history of Mars on this side. One of the lowest places on Mars, almost certainly this is filled with liquid water. So next slide, we end up picking Gale Crater, 96 miles across, rock layers, canyons, channels, all in one place. And here was our landing ellipse. This is a little scary. By the way, if we'd landed in this crater, game over, because we couldn't have climbed out of the walls. These are sand dunes. That got the scientists a little excited. We had to do a lot on Earth to prove that these sand dunes would not trap the rover forever, because that would be mission over 2. And we convinced ourselves we could drive between the dunes and get out of there if we landed there. Luckily, we didn't land there, but we don't have to test that hypothesis. Next slide, please. Okay, here's the evolution of the landing ellipse. This is impressive. This is good engineering here. This was the size of the landing ellipse at Viking. So Gale Crater is out the door. So 174 by 62 miles. And in the 2 years, or 2 decades, we didn't improve a whole lot. Pathfinder landing ellipse is down here, 125 by 44. Spirit of Opportunity, we improved a lot. Here's the Phoenix landing. Phoenix was a polar lander that discovered water and salt, water ice and salt. And it's not true that we were looking for tequila to make a margarita, but that's what the late night talk show said. And here is Curiosity's landing ellipse, a mere 12 by 4 miles. The star is where we landed, 1.5 miles from the center of the ellipse, after a journey of 352 million miles. Not too shabby. So, and of course, we're going to start heading up towards this crater right here. Towards the mountain right here. We're going to do a little dogleg to the southeast too, I'll talk about. But the way we've shrunk the landing ellipse is better Mars ephemeris, better navigation. We did a guided entry this time. With shuttle, when it comes in, it used to do bank rolls to shed speed. We did bank rolls and guided entry. We had a lifting body that came in the atmosphere, RCS thrusters, reaction control system thrusters out the back of the heat shield to do a controlled landing. And the only reason we were off by 1.5 miles is because we ended right at the end of a bank roll and couldn't really correct that air. And a little bit in the atmosphere too. Of course, the atmosphere is uncertain. It's tough to know exactly where you'll land. But isn't that impressive? And of course, scientists love this because the engineers want to land in the most flat, boring place in the universe because safety is #1 for the engineer. Scientists want to land, in the Grand Canyon on cliff walls and faces and things that make engineers lose sleep. So there's this healthy, good tension all the time between scientists and engineers. And the beauty is, if you get the landing ellipse small enough, they can both be happy. And that's where we're heading to. Next slide, please. Okay, so it picks up where other Mars rovers left off. We want to go beyond the water, look for signs of organics, carbon molecules, chain molecules. Next slide, please. Artist conception of what it might look like as we're climbing Mount Sharp, the different clay layers. Of course, I've got real pictures coming up later. Next slide, I'll go straight to those. Okay, here's the motor trend version of if you're in a road track, that kind of thing. The Curiosity by the numbers, 10 feet long, 9 feet wide, 7 feet high. So stereo camera, mast right here. It's like having an NBA player on Mars. They get about the same view, a 7-footer. Weighs about a ton, by far the biggest. That's on Earth. So Mars gravity is 3/8 of Earth, so it's about 750 pounds on Mars. The arm is 7 feet long, the geology arm. 20-inch wheels, titanium wheels, good cleats. They can climb 30-degree slopes. 10 science instruments. This is a big, bad, wicked rover. So Curiosity was named by a student from my home state of Kansas, a gal named Sarah Ma, wrote a beautiful essay, and I got to meet her at landing, which was just such a thrill. Next slide, please. Okay, science instruments. Let's talk a little about these since we're in engineering science kind of talk. Mast cam are the stereo cameras. We'll see that in a minute. These have long focal length capability and zoom capability. We have REMS, which is the temperature, pressure, wind speed measurements, the little things sticking off the neck of the rover. We have the ovens are here, SAM inlets and Kim-In inlets. These use spectroscopy, ground up a sample. We have drills. We have Molly is the microscopic imager at the end of the robotic arm. APXS, alpha proton X-ray spectrometer. My whole life is acronyms: MIT, JPL, NASA. APXS is just, sorry if I get lost in the alphabet soup there. Marty is the descent imager, Mars descent imager. Someone said, please let's put this on, because once the heat shield drops away, we can get a video of us landing. And they're like, that sounds like a PR trick. Well, maybe, but it gives us context for the landing site. Okay, you've sold me scientifically. So I'll show that high-def movie from the Marty. It's really cool. We have Dan in the back. This is a neutron mass spectrometer. It fires neutrons into the ground, measures water composition in the soil. RAD is that radiation detection instrument. These are some of the attachment points for the cables. Talk about that later. RTGs in the back, radioactive thermoelectric generator. I got a slide on that later. Telecommunications, I don't have a slide. I'll talk about that now. Ultra high frequency antenna right here that talks to the Martian orbiters, Odyssey and MRO, Mars Reconnaissance Orbiter and Odyssey, to relay data back. And 90-95% of our data is going to come back through this bent pipe relay from Martian orbiters. If you just had to rely on this high gain antenna right here, it would be much less data return. And that's true for the other two rovers that preceded it as well. Did I miss anything? Oh, ChemCam, my favorite. ChemCam is an infrared laser that can shoot from 30 feet away and vaporize rock. And then you measure. So tell the Martians we are armed this time. Stay out of the way. And then our spectrometers can pick up the gas cloud coming off the rock. And of course, the kids always ask, would the laser hurt you? And so I had to ask, do I found the right guy? Yes. If you got in the way, ChemCam would give you a very nasty burn. It's a pulse laser, but if you can vaporize rock from 30 feet, you're going to do a number on skin, too. Okay. Next slide, please. Okay, here's the family portrait. It's always tough to get them close together. Front steps of JPL. And here's Sojourner, microwave oven, child's wagon size. Here is Spirit and Opportunity, the Mars Exploration Rover's MER. And here's the big bad Curiosity. So that is a big, big rover. I just have this urge to jump on it and ride it. I know I get in trouble, but I want that photo on my Christmas card. It would be so cool. Next slide, please. Okay, this is a little hard to read, but this is the complexity of trying to get there. This is what our mechanical engineers might like this slide. So we've got a launch, which we did 2 days after Thanksgiving last year on an Atlas V from Florida. 9 to 10 month cruise, ended up being about 8.5 months. A spinning cruise stage to keep it stable on the way to Mars. We arrive in Martian Northern Hemisphere summer. Then the 7 minutes of terror, entry, descent, and landing, going from 13,000 miles an hour to 0 in 7 minutes. Not easy. Guided entry, controlled power, a very small landing ellipse, much smaller than it says here. We had to get 1,000 kilograms out of the surface. And then on the surface mission, we have prime mission is 1 Martian year, which is about 2 Earth years, about 23 months. And we, since we have RTGs, radioactive thermoelectric generators, we don't have to go near the equator. We can land north or south pretty far. Turns out we landed pretty near the equator anyway. 20-kilometer range, 12 miles of driving, that's a lot. 85 kilograms of science payload, that's about a factor of 10 higher than what we had before. Samples of rock, dozens of samples. Large rover, high clearance, greater mobility. We can rock climb and climb over big rocks. We can mountain climb. This is it's like having a true off-road vehicle, all-terrain vehicle on another planet. Next slide, please. Okay, Let's see, 17 cameras, laser, the Zaprox, and the drill. That's all. This is in our clean room environment. Next slide, please. So we'll zoom in on a couple instruments. Mast cam. This is the stereo image. Everybody here, if you can find it, go online, Google 3D glasses. You can get 3D glasses for 50 cents a pair. Literally that cheap. I encourage you to get a pair of 3D glasses. Get them for your family. 2 for $1, right? Whole family, even a Mormon family. We can get I'm Catholic, so we have the same. We get these about that too. So the cool thing then, Google 3D Mars. And then you can send it to your computer. In case you're not lucky enough to get to go to the red planet, you'll feel like you're on the surface there with those goggles. Okay, and so mass cam stereo imagery. Next slide. Okay, there's ChemCam. See, we're testing it. We got our laser. And I think my next chart is actually ChemCam being used on Mars. Let's see.
Next one?
Yeah. I'm actually a cat person and a dog person, so now if you're a dog person, you probably really find this funny. Maybe if you're no cats were harmed on Earth or in Mars, and if I found this on the internet, I just had to put it in my slide. So all kitties are safe on Mars. Okay. Next slide. Okay, thanks. So here's the little masts that look like little growths sticking off the neck of the rover. Those have the pressure and temperature, wind speed indicators. And this is in our clean room environment at JPL. So you can see the bunny suits whenever we're around. Very sterile environment, 10 or 20 times cleaner than a hospital surgery room, operating room. That's the word I was looking for. It's quite an ordeal to get in these clean rooms. There's a positive pressure gradient in the room every time you open a door. Clean air rushes out, and it's the exact opposite of that, like in Centers for Disease Control in Atlanta. You don't want to kill the nice people in Atlanta, so you have a negative pressure in the room every time you open a door. The air rushes in, so the microbes stay in there. So this you get an air shower. You suit up, you get an air shower, you get your feet scrubbed, you get electrically grounded. You walk in there, pressure and temperature and humidity are controlled very precisely in the room, and it's quite an ordeal. And I have to say, I've been in the clean room once. It was for the last Mars rover, and I know I wasn't supposed to, but I just had to touch something that was going to Mars. So I was like, I hope they don't still leave fingerprints. I got gloves on, but I was like, whoop, and it worked. So I didn't kill the mission, but I just had to touch something going to Mars. Okay, next slide, please. Okay, so 7-foot long arm. We've got the tools built in the hand. So we've got a drill, coring tool, a great hand lens, microscopic imager, all kinds of great things. Next slide. I think that's okay. Here are the rock analyzers, APXS, chemical elements in the rock. That's on the hand, and on the body are these ovens. ChemIn identifies the minerals, and SAM identifies the organics, and some part per million or even part per billion sensitivity. There's methane detector as well. So this is your chemistry lab, mobile chemistry lab. Until we can bring samples back from Mars, this is the best we can do. Next slide, please. Okay, this is our microscopic imager and an example. It has photos that we can do microscopic imaging at night, because we tend to park at night. We don't like driving at night. We don't have any floodlights or headlights or anything. So once we're parked, if we can do science at night, that could include illuminating sources and doing microscopic imaging. Next slide, please. Okay, here's RAD. It's on the side of the vehicle. We actually use RAD in flight because we're coming up towards solar maximum. So we were able to see some big solar flares and how they affected the innards of the spacecraft. But again, this is basically there for future human missions to characterize the Martian radiation environment. Next slide, please. Okay, here's our power source. This is an RTG, radioisotope thermoelectric generator. It's a nuclear battery, not a reactor. Plutonium-238. Not the most pleasant stuff in the world, by the way, but it's wonderfully benign in the sense of there's no moving parts. Moving parts in space is bad. That's what Frankenstein would say. Moving parts bad, because they tend to break in space. This has no moving parts. It's a reliable battery for decades. And the bad news is it's 100 watts of power. So the entire spacecraft have to run on a 100-watt light bulb worth of power. That's tough. All the science instruments, rovers, instruments, the heaters, the telecommunications. That's a challenge. It's also, I don't know what the price on this is, it's at least $50 million. That's kind of expensive for 100 watts, right? So it's not going to help solve the energy crisis, but it does make our lives really good. We've had trouble with our launches from Florida with these on board because of the RTGs. And if you spread plutonium finely and inhale it, it could do a lot of damage to the nice people of Florida. So we've had to show that even in launch accidents that RTGs are self-contained and don't release their plutonium. And that was fun. We had a lot of fun destructive testing. We set them on fire, blew them up, shot them with shotguns. We just could not get the plutonium out. And so that was really fun testing. Galileo launched on the shuttle in '89, and there were a few protesters trying to block our launch. And Cassini in '97 also had 72 pounds of plutonium, by far the most we've ever sent. And they had more protesters, hundreds and hundreds. I blame the internet. So they were able to organize more easily in '97 versus '89. So they came out, and a bunch of them climbed the fence and went and chained themselves to the launch pad, including this 82-year-old grandmother came out. And so she was starting to climb the fence. We thought, oh, this is such bad press. You know, she's going to break a hip or something. So we cut a hole in the fence for her, crossed, and then we could arrest Grandma. So and then before she could get to the launch pad. And now she's one of our biggest Cassini fans. So I'm not sure if she's still alive, but we turned her to our side. And we did have people take her out on launches. But I always like to tell the story of how we arrested Grandma after we cut the hole in the fence. Caught her for trespassing. Okay, next slide, please. Okay, we would love to scale up, reuse what we did for Opportunity and Spirit. Wouldn't that be great? That'd keep the costs down. And the problem is this rover's just too big and bad. So everything we tried failed. The parachutes failed. We needed a new heat shield, wider heat shield. The airbag landing didn't work anymore. The airbags would have to be too heavy and bulky and couldn't package and would have too much landed mass. So we had to find a new way to land. We were testing the parachute in Ames, NASA Ames in Northern California. Parachute ripped to shreds. So we had to go back to the design process and beef up. It's pretty tricky to pop a parachute in Mach 2.2. We don't have a lot of experience on it. So most of it comes from a prior Mars experience. But anyway, we eventually got the parachute working. It's like 66 feet in diameter, so it's a big, big parachute. Next slide, please. Okay, so then you got to put all this together in some kind of Rube Goldberg contraption. You need a heat shield up front, an ablative heat shield, probably carbon phenolic, more than half the mass of which will burn off in the atmosphere. The rover itself, a descent stage that can get the rover to the surface. I'll talk about that more. A back shell with the holes in it, with the RCS thrusters firing out the back, and then the cruise stage getting it to Mars. And the cruise stage is the part I worked most on, propulsion engineer, firing the rockets, keeping on course for Mars. I had a little bit to do with the descent stage, not too much. They don't like me near hardware. I tend to break things, so that's why I fly them and let them get launched, and I can't break them too easily. Next slide, please. Okay, how do we talk to our spacecraft? We have a NASA, underappreciated asset at NASA called the Deep Space Network, another acronym, DSN. And the DSN is a series of large giant radio antennas around the world, 120 degrees apart in longitude in 3 different locations. Canberra, Australia, Madrid, Spain, Goldstone, California. So no matter where your spacecraft is at any corner of space, one of those 3 antenna sites can see your spacecraft. And it's a very contentious resource. There's people's jobs, it is, just to help projects play nicely with each other and share the limited assets of the DSN. At each site, there's a 70-meter diameter, 230-foot diameter. That's big. That's a bigger area than a football field. And I've heard that you can move these by hand because it's on a film of oil a few thousandths of an inch thick. The mechanical engineering executive. They're out to azimuth control and can track spacecraft. So we have one 70-meter diameter at each site and 3 or 4 or more 34-meter diameters, half that size. And that's the bulk of the Deep Space Network. Amazing set of machines. It's been around since the 60s. We just did a refurbishment on the big one at Goldstone. And that was a nice PBS special about the mechanical engineering, about how do you lift up an antenna and fix the bearings there. Very difficult problem. Weighs a few million pounds, I think. Next slide, please. Okay, so here are 2 of our orbiters. The Europeans have one also called Mars Express. But Mars Reconnaissance Orbiter, Mars Odyssey, these have been around for about a decade out at Mars, a long time. They're well past their warranty, yet they're still working. They're sending most of the data we get from Opportunity, and now they're sending most of the pictures and data we're getting from Curiosity. Plus, they were instrumental during EDL itself. During entry, descent, and landing, the 7 minutes of terror, the Earth set, or we didn't have direct communication from the rover as it was landing. We did for a little bit, but not clear to landing. So if we wouldn't have had these orbiters in place relaying the signal, we wouldn't have known in real time that we survived. And that would have been bad, because we were, as you might imagine, it was a pretty sphincter clenching moment, if I can say that. But it was very, very nerve-wracking, because it's all happening on Mars 14 light minutes ago. So that means that, of course, it's already landed before you've even seen it hit the atmosphere, because it's only 7 minutes from the top of the atmosphere to the bottom. So it was all on autopilot, and we're waiting like the rest of the world. Praying, a lot of praying. Next slide, please. Okay, this is a still from our launch, and I think if we go to the next one's our first YouTube link, so we'll pull up the launch here. This is an Atlas V. We Mars and Earth line up every 26 months, every 2 years and 2 months. We have to launch.
15 seconds. 10, 9,
No
8,
video. There we go.
7, 6,
Full screen.
5,
tried.
4, 3, 2, 1. Main engine start, 0, and
Watch out, Birdie.
liftoff
Okay.
of the Atlas V with Curiosity. So you conclude with a planetary puzzle about life on Mars.
So this was 10 a.m. Eastern Time, Saturday after Thanksgiving last year. Beautiful launch. We were originally going to launch in September of 2009, and we just weren't ready. We had actuator problems, we had propulsion problems. I think if we had tried to launch then, we would have failed. So it's quite a good, it was hard to come back to NASA and say we need another, we only need another 6 months, but you got to wait 2 years, 2 months for the plants to run. So many of us went off the project, and hopefully we'll be around to come back on the project. So one of the scariest days of the mission, obviously, because any launch failure could take you out. The kids saw this today, it's coming back to Earth. I was like, no, that's a perspective, but it does look that way. We thought the same thing when we were watching last year. I want that telephoto lens. Whoever has that, that's a good camera down in Florida, because this is way out over the Atlantic by now. Any propulsion folks in the house? Aerospace propulsion. So notice the plume is expanding as we're getting, that's what the rocket guys notice. So the plume is, at sea level is like this, and then as you're getting towards vacuum, it's heading out and spreading out wider and wider. SRB, another acronym, Solar Rocket Booster. We probably know about that one in Utah, right? Because of the shuttle, the Viacall. You guys have been good at the space program. There we go. Generally, we recover those in the Atlantic Ocean. We do parachute, refurbish them, and that's good recycling.
Again, our United Launch Alliance cylinder, you got a true area.
I think that's good enough.
Okay.
I can't remember what's towards the end. Well, so they're happy, but they're not done yet because the upper stage has to fire and then release the spacecraft separation. So that's when the Atlas V people can start to party because their liability is done at that moment when they release the spacecraft in the right direction at the right speed. So this is a real movie of the separation because there's a camera on the Atlas upper stage. So there's the spacecraft, the solar panels of the cruise stage, rotating around, catching some sunlight.
Separation.
And we change the spin rate a little bit on the vehicle, which you can start to see the relative spin here of this guy. Reduce de-spinning it. So this spins at about 2 revolutions a minute, and that's the last human eyes have seen of the cruise stage.
It's a little bit slow.
I'm sorry I only have these on YouTube. I'm not, believe it or not, for a rocket guy, I'm not very good with technology, so I haven't figured out how to get these videos in my presentation yet. But anyway, that's cool. I remember seeing that live. And we're on our way. And then, even when you have a bad day, you said, I've traveled 1 million miles today, because it was 8.5 months, 352 million miles to Mars. And here's our heliocentric trajectory. They all look alike. Everyone studied Kepler's laws, right? The home and transfer orbit between Earth and Mars, here it is. So every 26 months they line up. We're looking down on the plane of the solar system, by the way. Here's the sun. Earth's nearly circular orbit around the sun. Mars, elliptical orbit around the sun. We can see that pretty well. And we had a launch period that's 24 days long. Our launch window was only a second, twice a day. So you have to launch within that second or you're due. So that's a little scary. The first rover, I missed launch. I was going to miss the second launch. It was June of 2003, and it was an opportunity launch. And my church choir got asked to sing in Carnegie Hall in New York. And I thought back and I said, launch happens 5 or 6 times in a career. Carnegie Hall is once in a lifetime. I said, you can fire me, but I'm going to Carnegie Hall. And as it turned out, we didn't launch anyway. We had some launch delays. One of them was a fishing boat. So a fishing boat got out in the Atlantic and was in the path during the 1-second launch window. And I did not hire the fishing boat guy, but I remember singing Carnegie Hall and running around New York City and trying to find a TV. Did we launch? Did we launch? And luckily, it was delayed another week or two, so I was fine. I made the right decision. You know, it wasn't popular, it was a little risky, but no regrets now. So something to think about, you know. But always do your classwork and, you know, listen to your professors. But okay, so let's go back to this one. So the launch period was, we launched on day 2. We didn't actually launch the 25th, it was the 26th, the Saturday. Used all our launch energy to speed up. Of course, it's like BYU football game tonight, right? So your quarterback doesn't go fire at the receiver, fires where the receiver will be. That's what we did. So we fired here. Mars was here at launch. We were here. We got on this 8.5-month path to Mars, and then Mars was here at arrival, Earth was here at arrival, and this was our path out to Mars. So TCMs are trajectory correction maneuvers. That was my biggest job on the project. It's like a par 6, 352 million mile golf hole. You've got 6 chances to correct your path along the way. You remove the launch bias in TCM 1. TCM 2 was pretty small. 3 was even smaller. 4 was really tiny, and we canceled 5 and 6. And arrived at Mars August 5th of this year, 3 weeks ago. Okay, next slide, please. Okay, now how do we get from 13,000 miles an hour, which is what a Hohmann transfer gives you when you hit the Martian atmosphere, to 0 with very little atmosphere to help you, you know, in 6 or 7 minutes? That's not easy. Well, this is what they came up with. Separate the cruise stage. Throw off the balance devices so you get a lifting body. Enter the atmosphere. Peak heating, peak deceleration. Hypersonic entry phase. Aero maneuvering. Shutting back and forth. Flying out some of the speed. Supersonic parachute. Heat shield separation. Start collecting radar data on the ground so you know where the ground is. Separate the back shell. Then the descent stage and rover come down as a group under powered flight. 8 descent engines, each like 600 pounds of thrust. Power descent, as you're getting lower, slower and slower. When you're 66 feet from the ground, 20 meters, do the sky crane maneuver. Lower the rover on cables. That's what's crazy. Wait till you're down to the ground, cut the cables, fly off, crash the cruise stage. Here's the detail on the sky crane. And Wile E. Coyote would love, of course he's green because he's on Mars, but genius, he would have to love this. But of course his stuff never works. That's what scared me about putting this slide up before. As the Roadrunner always gets away, but we got the Roadrunner this time. Next slide, please. Okay, who has seen 7 Minutes of Terror before? Okay, it's only about a quarter, so I think we'd show the first video. It's about 5 minutes long. But they did a pre-landing video just to show how hard it was to set expectations low, because there was a very good chance we were
Crazy. It's a very natural thing. It is the result of reason thought. It still looks right. The top of the atmosphere. Now, the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away. So, when we first get word that we touched the top of the atmosphere, people are Mars. Today, on the surface.
Melodramatic.
After the second landing, also known as EDL, referred to as 7 Minutes of Terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, from 13,000 miles an hour to 0. Perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from here. If any one thing doesn't work just right, it's game over. Standing in the atmosphere, we feel so much aerodynamic drag out. It's up and it blows like a 1,600 degrees.
It's not only slowing down violently through the atmosphere, but also we're guiding like an airplane to be able to land in a very narrow constraint. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So that might be the parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
It opens up that fast. It's a neck snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we got, it only slows down to about 200 miles an hour. And that's not slow enough to land. So we have no choice. We have to pay off and come down in rockets. Once we turn those rocket motors on, we don't do something. We just smack right back into the parachute. So the first thing we do when it was really radical, we fly off to the sun. Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting it over, moving straight up and down so we can look at the surface of this radar and see where we're going to land. Looking straight down to the bottom of the crater, right beside a 6-kilometer island.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively, our engines all the way to the ground, we essentially create this massive dust cloud that then goes and land on the rover with the damaged mechanism and the damaged instrument. So the way we solve that problem is by using the sky wave.
20 meters above the surface, we have to lower the rover below us on our tether. It's 21 feet long, and then gently toss it on its wheels, on the surface.
As the rover touches down and is now on the ground, in the same state, it's in a collision course with the rover. We must catch the driver immediately and fly to the same state to a safe distance from the rover.
Go wrong, right? Okay, let's skip that second one. Okay, now we're on landing day. This is a real photo, definitely in my top 3 favorites so far from Curiosity. Our Mars Reconnaissance Orbiter with the 1-foot resolution, we realized if we were really lucky, about a 50% chance, we'll point down our best knowledge of where the rover is during entry, descent, and landing, towards the end of the parachute flight before we do the back cell separation. We caught this raw photo right here, and here's the blow up. So that is a real photo of Curiosity coming down during the 7 minutes. Absolutely stunning picture. The parachutes, this would have been useful for anomaly diagnosis. You know, if the parachute had squidded up or was in some strange shape, we'd say, well, that's what killed us, instead of all the other things that could have killed us, right? So this is great. Next slide, please. Okay, this is a real picture. This is from the Marty, the descent imager in high def, and that's after we dropped the heat shield away. Remember the sand dunes I talked about that we were afraid of landing in? They're right down there. Next slide, please. And I think now I've got a little short movie, a couple minutes long, of the high def from Marty, the descent imager itself, from releasing the heat shield down to the surface. And they've integrated it with the audio commentary from Mission Control. So this is what was happening in real time. Three minutes, that's not too bad. Gotta watch my time a little bit. And we see nothing because we have a red cap on. The heat shield's, there it goes. See the wind's bumping us a little bit? Things are jostling.
Come back again with wrist mode dynamics.
Wrist mode, that's this kind of swinging back and forth on the parachute. It wasn't too bad. So they're following all that in real time.
Medical is converted to the velocity range of 0.2.
decided to ground with the radar.
So the radar found the ground, that's good. You can't land without that.
Found the ground. Due to Earth location as expected. We're getting by in front of the Emily engine in preparation for power play.
So Earth occultation, we're going to lose a direct signal.
Second, at an altitude of 6.5
And
kilometers.
then everything was relayed through Mars Odyssey. So thankfully that relay worked, or we wouldn't have known from this point until days whether we landed or not.
Flight video, we've got video warnings. I didn't think that when we was low station out of direct Earth communications at the time. We may have lost our way.
That's expected.
We're down to 86 meters per second at an altitude of 4 kilometers descending.
So 20,000 feet, 200 miles an hour. The rocket's
We've lost zones from Earth at this time, as is expected. We're continuing on autopilot here.
Crash dilution equals minus 10.8 meters, vertical velocity of minus 80.
We are on the 8 meters light start enabled, standing by for vaginal separation.
So we're about to drop
Signal
out.
velocity is still strong.
We are in higher flight.
Okay, rockets are firing now.
We're at an altitude of 1 kilometer descending, about 70 meters per second.
Signal velocity is
About 50 meters per second. 500 meters altitude.
1,600 feet.
Standing by for Skytrain.
Constant velocity accordion nominal, altitude error 5.9
Watch
meters.
for the rocket plume. It's there. See, it's starting to kick up dust on the surface there.
Down to 10 meters per second. 40 meters altitude.
And there's the wheel. See it pop out after Skytrain?
Skytrain started. Descending at about 1.75 meters per second as expected. Expecting
0.75 meters per second. That's not too bad, huh?
Signal velocity
Like laying a baby down in a crib. It's dark now.
Tango Delta nominal.
Tango Delta, touchdown, nominal. Okay, that's the first clue. Then we wait to make sure we still have communication.
Yes.
So,
You go on configuration stable.
configuration stable. And then we make sure that the descent stage has crashed and didn't land on top of us. And there's the rocks.
Yeah, that's good. Touchdown. Proceed.
And within 5 minutes, in mission control, this pops on our screen. Not the best photo. First of all, there's a lens cap on the hazard avoidance cameras, so that's why there's so much dust kicked up. But within 5 minutes, well, we know we're on a solid body. We can see that. Here are the wheels. There's the sun. That's funny, this triangular shaped thing. I'll come back to that in a slide or two. But this was maybe your favorite photo because you know you're safe and on the surface. Although, within 5 minutes, the next slide came up. So we get the shadow of the rover in the late afternoon sun, and there's Mount Sharp, the 16,000-foot mountain off in the distance. Still with some dust on the lens, but not too bad. Better sun angle here. Next slide. Okay, now as it turns out, we took this picture, and that little triangle thing was there 20 seconds after landing, but not 40 seconds after landing. Or vice versa, I forget which. Well, I think the former. That's the crash of the descent stage. We happen to be pointing away, and we see the giant kaboom. Of course, Marvin's happy because he loves giant kabooms, so he needs to mellow out. And here we are, off about a third of a mile away or so, very safe distance from the rover. But we caught that up towards the sun. Next slide, please. Okay, and then as the high resolution started coming, or maybe we faked the whole thing in Utah, Nevada, or California, but we didn't. Here's the view of these distant, gorgeous mountains, self-view of the rover. There's some rocks up on the rover that were kicked up by the exhaust. That's okay. They're not in the way of the science instruments and the ovens and all that, so we're still good. Next slide, please. Okay, here's the crime scene photo from orbit. Kind of prove that we landed there. Here's the heat shield that dropped off first, and then the parachute and back shell over here. Curiosity is right in the middle of this. It's the discoloration is due to the rocket plume exhaust, and that says Skytrain. It's really the debris from the sky. It hit it out here, and, you know, oblique impact, and headed this direction and left a nice smoking hole. Okay, next. Oh, let's go back. I want to show one thing here. Our first science target is right here. Now, see, there's 3 different kinds of terrain here. Scientists love that, the diversity. You get this kind of smooth terrain, and this is a little rougher, more cratered, and then this whitish terrain. They all meet about here. So we call this Glen Elg. if we drive there, we can sample at the same spot all three kinds of terrain at once. And it's only 500 yards away, 5 football fields away from Curiosity. So that's our first destination. We should be there within a few weeks, actually. Next slide, please. And this is a color shot showing the rocket plume and how it's discolored everything. See that there, right there, though? That's the rover. The rover's big enough, it's a few pixels across. So that's really a nice shot. Okay, next slide. So this is one of the most colorful parts of Mars we've ever been to. It's just beautiful. So we're starting to get good color images, high resolution images.
Is that natural color?
Natural color. Next slide, please. And these are the rocket marks. See the twin rockets here? It's propulsion, doing a little science. We excavated for them, and they're very excited. They're like, why drill? Why dig? The rockets have done some digging for us. We're going to go under there, look at the exposed bedrock underneath. So that's one of our first destinations too. Actually, we're already there. We're doing science there right now. Next slide, please. Self-portrait of the rover. It's got a nice tall neck so it can look 360 degrees, look down on itself, and it can get a self-portrait of the wheels and all these science instruments. There's the nuclear battery in the back, and look at that beautiful vista off in the distance here. Absolutely gorgeous. And I think the next picture may be, it's hard to say, but maybe my favorite picture from planetary science so far in 50 years of exploration. Next slide. Nope, sorry. These. That's not it. This is good though. 1.2 miles across here. These are the distant layers of Mount Sharp. And as good as that is, I think the next one has the layering and the color I'm looking for. That's it. Look at that. Isn't that absolutely beautiful? So this is within a few tens of feet of the rover, a few hundreds of feet. This is down 1 kilometer or 2 away, and this is 6 or 7 or 8 kilometers away. But we're going there. We're going to start reading the layers and all these rocks. This is what reminds me of the Grand Canyon, the layering. This is exactly what we see from orbit. That's why we went there. Look for the clays and the sulfates and read the geologic history of Mars. Impact readers give you that for free. They give you a time machine because of the different layering, just like we see in the Grand Canyon, different layers of different epochs. So we can't wait to get there, but that image is absolutely sublime. Next slide, please. Okay, you've arrived when you start getting lampooned in the national culture. If any of you have seen Stephen Colbert and Jon Stewart, they lampoon us really well right after landing. I got the front page of the LA Times, top fold. That's a picture that's on the screens out there that I've been seeing. I had to get a picture of that too from a Christmas card. That was pretty fun. And then I think one of Stephen Colbert's things, we all had the blue shirts in Mission Control. You saw those. And it was nice of them to give the day off from Best Buy so they could go land that. So that was a pretty good piece. So I'll walk you through a couple of cartoons. I'm running just a pinch late. So we have a evil-looking Mars waiting to parachute here, talking to Earth. That's right, keep sending probes over here. My super robot only needs a few more pieces before it's complete. This one's going around all Monday. Your excuse on Monday the 6th. Sorry, I was up all night trying to download photos taken by a robot lowered onto Mars by a sky crane. Yeah, right. No, it's absolutely true. Okay, here's the landings. We made it through 7 minutes of terror, a couple aliens. How long will it take you to eat it? About 7 minutes. So thankfully that didn't happen. Here's Curiosity landed on Mars. We should have put the club on it or a low jack because here are some Martians putting us up on concrete. Here is Mad Marv's used rovers. Runs like new. What's that say? Only 120 million miles on it. He's that's so even used car salesmen, can't get away from on Mars. This is Spirit or Opportunity. It's being stripped for parts by the Martians. Run! Here comes its mother. So that's pretty scary. We have the Martian Olympics. We actually have more people watching us in the Olympics, which I thought was amazing. Much to NBC's chagrin. Of course, we couldn't help but tease NBC a little bit. They have a 6-hour delay for an event 3,500 miles away, where we had a 14-minute delay. Okay, we have Marvin the Martian making a little appearance here. We have the INS agent on Mars, show me your papers. Another illegal alien coming in. And then this last one is, of course, what the Martians would want us to see. Not the cities in the background. Okay, next slide. I think we're done. Mars.jpl.nasa.gov/MSL. You can learn much more. We're on Twitter. We're on Facebook. Be a Martian's a really fun website. Just type in beamartian.jpl.nasa.gov. If you get totally lost, just go to nasa.gov. MSL is getting all the press. Or if you remember the /MSL, you can go straight there. Thank you for your attention today. I'll take your questions. I'm running around.